What happens when engineers deliberately sacrifice armor to build a combat vehicle? Most experts believed this project was doomed from the very beginning. Why did Sweden take such a huge risk? What critical compromise was hidden inside the IKV-72? And why was the army forced to redesign the vehicle only a few years after it entered service? Stay until the end, because you'll discover why this seemingly fragile machine became one of the most important milestones in Swedish armored vehicle history. If you're interested in tanks, secret military projects, and forgotten war machines, be sure to subscribe to the channel and turn on notifications. There are many more fascinating stories ahead. Enjoy the video, and let's continue. After the end of the Second World War, many countries began to massively expand their fleets of heavy tanks, betting that thick armor and large-caliber guns would become the main argument on the battlefield. But Sweden looked at the situation differently. The military understood perfectly well that their army, which would have to defend its own territory with its forests, swamps, narrow roads, and rocky heights, would not always need a huge and heavy vehicle. Far more often, the infantry required fast, armored support capable of appearing in the right place at the right time, destroying a fortification or firing point, and just as quickly changing position. The experience of the recent war years showed that even the most powerful tank was not always the best solution. A vehicle weighing over 40 tons experienced serious difficulties on weak bridges and forest roads, required large amounts of fuel and complex maintenance. For a country adhering to a policy of armed neutrality, such an approach looked too costly. The Swedish military needed completely different equipment, significantly lighter, cheaper, and capable of accompanying motorized infantry in almost any conditions. At the same time, requirements for the armament itself were also changing. The army was no longer satisfied with an ordinary light, self-propelled gun with a small caliber cannon. The new vehicle had to confidently destroy permanent fortifications, field structures, light armored vehicles, and armored personnel carriers, and, if necessary, pose a threat to medium tanks of its time. At the same time, the developers understood perfectly well that it was practically impossible to simultaneously achieve high protection, powerful armament, and low weight. So they had to look for a completely different balance. Another important factor was Swedish industry. After the war, it was actively developing, but it did not have unlimited production capabilities. The simpler the design, the faster production could be established. That is why, already at the requirement stage, engineers tried to make maximum use of existing technological solutions instead of creating a completely new platform from scratch. This approach shortened development time, reduced production costs, and facilitated subsequent maintenance of the vehicles in the troops. The military formulated a fairly specific set of requirements. The future vehicle was to have a mass of about 8 tons so that it could freely cross most bridges and move confidently over rough terrain. The maximum speed had to exceed 50 kilometers per hour, allowing it to accompany mechanized units without falling behind. The range had to be at least 200 kilometers so that the equipment could perform tasks without constant refueling, even in conditions of limited infrastructure. Special attention was paid to the silhouette. The lower the vehicle, the more difficult it was for the enemy to detect it among folds of terrain or forest. Therefore, the designers immediately aimed for the lowest possible hull with minimal height. At the same time, the crew was reduced to 4 people, distributing duties among the driver-mechanic, commander, gunner, and loader. This solution made it possible to maintain high efficiency of the crew without increasing the dimensions of the hull. From the very beginning, something else was clear. For the sake of high mobility, armor thickness would have to be sacrificed. Instead of heavy multi-layer protection, it was planned to use relatively thin armor plates, designed primarily for protection against small arms, fragments, and light automatic cannons at long ranges. This approach fully corresponded to the future tactics of use. The vehicle was not supposed to conduct prolonged duels with enemy tanks. Its main task was rapid deployment to a firing position, delivering an accurate strike and immediate withdrawal before the enemy had time to return fire. In fact, the Swedish engineers began to create an entirely new class of combat vehicle, situated somewhere between a light tank and a self-propelled artillery mount. On paper, this concept looked quite convincing. It promised to combine the mobility of light vehicles with the firepower of significantly heavier machines. But very soon it became clear that putting such an idea into metal would prove much more difficult than formulating requirements at military meetings. Once the general requirements were approved, the work moved to a completely different plane. Now, the engineers had to not discuss theory, but solve dozens of complex technical problems, each of which directly affected the future combat capabilities of the vehicle. It was at this point that it became clear that creating a light, self-propelled gun with high mobility and powerful armament was significantly more difficult than an ordinary tank of similar weight. The main developer of the project was the company Landsverk, which already had extensive experience in creating armored vehicles. However, this time, the designers decided to abandon many conventional solutions. Instead of a rotating turret, a fixed armored casemate was chosen. This step made it possible to noticeably reduce the overall weight of the vehicle, lower the silhouette height to almost 2 meters, and at the same time install a significantly more powerful gun without a substantial increase in chassis load. In addition, the absence of a turret mechanism freed up internal hull volume, which could be used for ammunition stowage and crew workstations. The basis of the project was a maximally compact chassis with front-mounted transmission and drive wheels. This layout allowed for more rational weight distribution across the hull and facilitated maintenance of the units. In the rear part, a Ford petrol engine with about 145 horsepower was placed. For a vehicle weighing about 8 tons, this provided a power-to-weight ratio of about 18 horsepower per ton, a quite respectable figure for the early 1950s. It was thanks to this that the IKV-72 was to accelerate quickly, climb slopes confidently, and maintain a high average speed over rough terrain. Much attention was paid to the running gear. On each side, 6 small-diameter road wheels with individual torsion bar suspension were installed. This solution provided relatively smooth running even on rocky ground and allowed acceptable firing accuracy to be maintained after short stops. The upper run of the track was supported by several return rollers, and the track itself had a relatively small width sufficient to reduce ground pressure without a noticeable increase in weight. No less challenging was the crew layout. The driver mechanic was placed in the front left part of the hull. To the right was the transmission, and behind them was the fighting compartment. The commander occupied the place to the left of the gunner to the right, and the loader worked in the rear of the casemate, next to the ammunition racks. This scheme reduced the time for passing shells to the breech of the gun and provided sufficiently convenient interaction between crew members even in the limited internal volume. Engineers paid special attention to visibility. Instead of large observation turrets that increased the height of the vehicle, compact observation devices with armored glass and periscopic devices were used. This made it possible to maintain a low silhouette and at the same time provide all-round situational awareness without leaving the protected volume. For its time, such a layout was considered quite modern, especially considering that the vehicle was created primarily for ambush operations and fire support. The engineers immediately understood that a fixed casemate imposed serious limitations. The horizontal traverse of the gun was only a small sector on either side of the vehicle's longitudinal axis. If the target moved outside this sector, the driver mechanic had to turn the entire hull. This increased reaction time, but allowed the elimination of the heavy turret ring, complex traversing drives, and additional turret armor. The weight savings amounted to hundreds of kilograms, which could be used much more rationally. As a result, an unusual vehicle gradually began to take shape, completely unlike most tanks of the time. It did not try to compete with them in armor thickness, and did not seek to replace full-fledged self-propelled artillery. Instead, the Swedish engineers were creating a compact, fast, and relatively inexpensive combat system where almost every technical solution was subordinated to one goal: to deliver a powerful gun as close to the front line as possible, ensure a quick, accurate strike, and withdraw the vehicle from under return fire before the enemy could take advantage of their superiority. And it was here that the main question arose. If the design already looked quite unusual, what weapon were they going to arm this light vehicle with so that it would truly live up to expectations? The answer to this question lay at the very heart of the project. All previous technical decisions existed for only one purpose: to mount on a relatively light chassis such armament that would give the vehicle real value on the battlefield. That is why the developers began not with the search for the most powerful gun, but with the selection of a system that combined sufficient firepower, acceptable weight, and reliability. As the main armament, a rifled gun of 75mm caliber was chosen, specially designed for this vehicle. The barrel length was about 50 calibers, which provided a sufficiently high muzzle velocity and good trajectory flatness. Compared with shorter-barreled guns of the wartime period, such a weapon significantly more confidently engaged targets at medium ranges and allowed the crew to open fire earlier than the enemy could close the distance. Several types of ammunition were immediately developed for the IKV-72. The main type was the high-explosive fragmentation shell, intended for destroying field fortifications, machine gun nests, and light defensive structures. Such targets were considered a priority for infantry support. In addition, armor-piercing shells were used, allowing engagement of light armored vehicles and certain types of medium tanks of the early post-war period, with a favorable choice of range and impact point. The ammunition load was about 40 rounds. The stowage was located along the inner walls of the fighting compartment and in the rear part of the casemate. This arrangement allowed the loader to work as quickly as possible without making unnecessary movements in the cramped space. With good crew training, the rate of fire could be maintained at up to 8 rounds per minute, which was a very high figure for a vehicle of this class. The designers also paid great attention to the gun carriage itself. Despite the compact dimensions of the vehicle, the mount received effective hydraulic recoil mechanisms that absorbed a significant part of the shot energy. As a result, after firing, the hull did not experience excessive shock loads, and the gunner could more quickly return the sight to the target for the next shot. For a light vehicle weighing about 8 tons, this was fundamentally important, since too strong recoil could negatively affect both accuracy and structural service life. The vertical traverse angles were also selected with regard to the features of the Swedish terrain. The gun could confidently depress and elevate to a fairly large angle, allowing fire from behind natural cover as well as from elevated positions. In hilly terrain and dense forests, such capability significantly increased the vehicle's survivability. It was enough for the crew to expose only the upper part of the casemate and the barrel above the cover, leaving most of the hull concealed. Aiming was carried out through an optical sight with variable magnification, designed for confident engagement of point targets at distances exceeding 1,000 meters. No electronic computers, laser rangefinders, or stabilizers existed at that time. Therefore, accuracy depended entirely on crew training, correct range estimation, and the gunner's skill in applying corrections. That is why the Swedish Army placed particular emphasis on crew training. Another feature was the absence of a muzzle brake. This solution reduced the unmasking effect of firing. The raised dust cloud became significantly smaller, meaning it was harder for the enemy to immediately determine the exact location of the self-propelled gun. For a vehicle whose tactics were based on a short fire raid followed by a change of position, such a detail played far from a minor role. However, even the most successful armament could not fully compensate for the limitations inherent in the design from the very beginning. While engineers strove to achieve maximum mobility and high firepower, they had to make very serious concessions in another direction. And it was precisely these compromises that soon began to raise more and more questions from both testers and the military themselves. When the first prototype vehicles began undergoing trials, it became obvious that for impressive mobility and powerful armament, a rather high price had been paid. Many compromises that had seemed fully justified on the drawing board proved much more noticeable in real operation than the developers had anticipated. The main sacrifice was armor protection. The frontal hull had a thickness of only 18 millimeters, while the sides and rear were protected by armor plates about 7 millimeters thick. Such armor reliably protected the crew from rifle bullets, artillery shell fragments, and occasional hits from light, small arms, but heavy machine guns and automatic cannons already posed a serious threat to the vehicle. Encountering a full-fledged tank gun left virtually no chance of remaining combat effective. The design features also imposed their own limitations. The frontal armor plates were placed at rational angles of inclination, which somewhat increased the likelihood of ricochet. However, the small thickness of the metal remained the main weak point. When hit by an armor-piercing projectile, the impact energy was often so high that even unpenetrated armor could produce dangerous spalling on the inside, creating an additional threat to the crew. Another important feature was the fixed casemate. Although it allowed a significant reduction in vehicle weight and the installation of a relatively powerful gun, the limited horizontal traverse seriously affected tactics. When a target appeared from the side, the driver mechanic had to turn the entire hull, and this took precious seconds. If the enemy spotted the IKV-72 first, such a delay could be critical. The compact dimensions of the vehicle also had a downside. The internal volume of the fighting compartment turned out to be quite restricted. During intense firing, the loader had to work with almost no free space, constantly moving between ammunition racks and the breech of the gun. After several minutes of active combat, the rate of fire inevitably decreased simply because of the crew's physical fatigue. Certain questions also arose regarding the power plant. Although the petrol engine provided good dynamics, it consumed significantly more fuel compared to similar diesel engines, which were gradually becoming the standard for armored vehicles. In addition, A petrol power plant imposed higher fire safety requirements. When the engine compartment was damaged, the risk of fire increased significantly, so the crew had to make maximum use of the advantages of high speed and not linger under fire. The tests also revealed features of the suspension operation. The torsion bar scheme coped well with rough terrain and provided smooth running, but when moving at high speed over severely uneven ground, significant loads were imposed on the road wheels and suspension elements. This required regular maintenance and careful monitoring of the running gear after prolonged marches. Another feature was the absence of any collective protection system for the crew. In the early 1950s, such equipment was not yet considered mandatory for light armored vehicles, but with the development of new types of weapons, this shortcoming gradually became more and more noticeable. The vehicle was designed in accordance with the concepts of its time, but military science was developing much faster. As a result, the Swedish Army received a vehicle that had very clearly defined strengths and weaknesses. It was fast, compact, had decent firepower, and was ideally suited for sudden fire raids. But any crew error, delay in the open, or attempt to engage in prolonged combat with heavier armor almost immediately negated these advantages. That is why the command had to very carefully think through the tactics for employing the new self-propelled gun. And when the IKV-72 finally began to enter line units, it became clear that real service would reveal much more about the vehicle than any factory trials. The first production IKV-72s began to enter Swedish Army units in the early 1950s. For the military, this was not just another piece of armored equipment, but an opportunity to test a completely new concept in practice. Instead of a heavy vehicle capable of withstanding prolonged enemy fire, the troops received a light, self-propelled gun whose success depended entirely on correct position selection, proper coordination with infantry, and speed in changing firing positions. Almost immediately, crews began to master new tactics. The vehicle was rarely used in the first echelon of an offensive. Far more often, it occupied pre-prepared positions from which it could support infantry with fire while remaining partially concealed behind folds of terrain, large boulders, or forested areas. Thanks to its low hull, the IKV-72 was significantly easier to camouflage than most tanks of the period. This was especially valued in the Swedish landscape, where natural cover was abundant. During operation, another advantage of the vehicle was confirmed: high operational reliability. Most of the units were designed with maintenance in the field in mind. Access to the engine was provided by large rear hatches, and many transmission elements could be replaced without fully dismantling the hull. This reduced repair time and allowed the vehicle to be returned to service more quickly after faults were detected. Standardization of parts also played a big role. Some running gear and powertrain components were maximally standardized with other Swedish armored vehicles. This approach simplified the supply of spare parts and reduced the burden on repair units. For a small army, this was of great importance, since it allowed the range of warehouse stock to be reduced and maintenance to be accelerated. During long road marches, crews noted the successful weight distribution of the vehicle. Despite its compact dimensions, the load on the road wheels was distributed fairly evenly, which had a positive effect on the service life of the running gear. On soft ground, the self-propelled gun confidently maintained mobility, and its relatively low weight allowed it to cross sections where heavier armor risked losing speed or even getting stuck. At the same time, military operation revealed features that could not be detected at the factory test ground. In the confined fighting compartment, temperature rose rapidly during intense firing. Engine operation, heating of recoil mechanisms, and propellant gases created far from comfortable conditions for the crew. Therefore, the ventilation system, which removed gases after each shot, became very important. Without its effective operation, the rate of fire quickly decreased due to deteriorating conditions inside the vehicle. Communication quality also proved important.
Each self-propelled gun was equipped with a radio set that allowed constant contact with command and adjacent units. It was thanks to reliable radio communication that crews could quickly receive new target coordinates, change positions, and act jointly with infantry. For a vehicle whose main task was fire support, timely information exchange was no less important than the characteristics of the gun itself. However, time did not stand still. Within just a few years of the IKV-72's adoption, the development of armored vehicles worldwide accelerated. New tanks received thicker armor, anti-tank weapons improved, and requirements for firepower and artillery effectiveness rose. A vehicle that had recently looked modern was gradually beginning to lag behind newer designs. The Swedish command carefully analyzed operational experience and concluded that the concept itself had proven successful. The light, mobile, self-propelled gun had fully justified itself as an infantry support vehicle. But at the same time, it became clear that further service would require serious modernization. And it was then that a decision was made that effectively gave the IKV-72 a second life, turning it into the basis for a much more advanced combat vehicle. Operating experience gradually formed a fairly clear picture. The IKV-72 had fully confirmed the viability of the concept of a light, self-propelled infantry support gun, but at the same time revealed the limits of its further development. The more time passed, the more clearly it became evident that the main problem lay no longer in the chassis design, but in the capabilities of the armament. Over several years, the armor protection of modern tanks had increased noticeably, and the capabilities of the 75mm gun were becoming insufficient for confidently solving some combat tasks. Swedish specialists carefully studied the results of training firings and concluded that there was no need to completely replace the vehicle. The chassis itself had a good margin of reliability. The engine and running gear continued to demonstrate satisfactory performance, and operating costs remained significantly lower than those of heavier armored vehicles. Therefore, it was decided not to develop an entirely new self-propelled gun, but to carry out a deep modernization of the existing design. The main focus of modernization was armament. The new vehicle received a rifled gun of 105mm caliber. Compared with the previous gun, the projectile weight increased significantly, and high explosive fragmentation effect became substantially more effective. Now the self-propelled gun could much more successfully destroy permanent fortifications, stone structures, and field defensive positions, for the sake of which it had originally been created. Installing a more powerful gun required serious reworking of the internal hull structure. The carriage mountings were reinforced, the recoil mechanisms were modified, and the ammunition racks were redesigned, since the new rounds had significantly larger dimensions. At the same time, the balance of the entire front part of the vehicle had to be adjusted to maintain acceptable suspension loading and not impair handling. Changes also affected crew workstations. New sighting devices provided more convenient operation for the gunner, and the commander received improved observation means. Although modern electronic fire control systems were still absent, the quality of optics had noticeably improved compared with the original vehicle. This positively affected first-round hit probability, especially when firing at longer ranges. After the modernization was completed, the upgraded self-propelled gun received a new designation, IKV-102. Formerly, it was considered a further modification, but in terms of its capabilities, the vehicle already differed noticeably from the original IKV-72. In effect,
the Swedish engineers had managed to preserve all the strengths of the original design while eliminating one of its most glaring shortcomings. This step finally confirmed the correctness of the concept chosen as early as the beginning of the 1950s. Instead of abandoning the project after the first limitations appeared, the Swedish Army decided to develop it further, and it was precisely thanks to this approach that the history of the IKV-72 did not end after a few years of service, but became a starting point for the emergence of a whole family of more advanced vehicles. Gradually, it became obvious that the significance of the IKV-72 was measured not by the number of units produced or participation in military conflicts. Its true value lay in something quite different. Decades later, armored vehicle historians increasingly call the IKV-72 one of the most underrated Swedish combat vehicles of its time. The reason is quite simple. This self-propelled gun almost never took part in major armed conflicts, did not gain worldwide fame, and was not produced in huge series. However, it was on this vehicle that Swedish engineers tested many technical solutions that later became the basis for subsequent projects. Working on this vehicle, the designers gained a huge amount of practical information about weight distribution in light armored vehicles, torsion bar suspension performance at high speeds, low-profile hull layout, and placement of armament in a fixed casemate. Many conclusions drawn during the operation of the IKV-72 were later used in the development of the next generations of Swedish combat vehicles. No less important was the accumulated operational experience. The Army was able to assess the real advantages of high mobility over simply increasing armor thickness. During numerous exercises, it turned out that a properly chosen position, good camouflage, and rapid change of firing positions were often significantly more effective than attempting to sustain a prolonged exchange of fire with a heavier opponent. The designers also became convinced of the great importance of the ability to modernize existing equipment. Instead of creating a completely new vehicle, it was possible to use the existing chassis, substantially reducing program costs and rearmament timelines. Later, this principle was repeatedly applied in the creation of other Swedish armored vehicles. If one looks at the IKV-72 today, it becomes obvious that it cannot be assessed solely by armor thickness, engine power, or the caliber of its original gun. These indicators quickly became obsolete. The vehicle's real achievement was its engineering philosophy. The Swedes showed that even a relatively light self-propelled gun could effectively perform its task if every detail of the design was subordinated to a single tactical idea. That is why the IKV-72 remains an important page in the history of world tank building. It did not become a legend like the most famous tanks of the 20th century, but it managed to accomplish a far more complex task. This small vehicle proved that sound engineering calculation, well-thought-out tactics, and continuous design improvement could bring an army far more benefit than a simple race for maximum weight, armor thickness, or gun size. And it is precisely with such, at first glance, unremarkable projects that the emergence of truly outstanding armored vehicles often begins. When people recall Swedish tank building today, the conversation usually quickly shifts to far more famous vehicles. Against their background, the IKV-72 easily remains in the shadows. But if one looks closely at its history of creation, it becomes clear that it is precisely such projects that often have the greatest influence on the development of military technology. This self-propelled gun was never created as a universal tool for all combat conditions. It was designed for a very specific task: to deliver a powerful gun to the right point as quickly as possible, support the advancing infantry, destroy a fortification or enemy firing position, and immediately leave the dangerous area. That is why virtually every engineering decision was subordinated to one common idea. Low weight facilitated the transfer of equipment between defense areas. A low silhouette simplified camouflage. Simple construction reduced operating costs. And the possibility of further modernization allowed the service life of the vehicle to be extended without creating a completely new model. Over time, this approach became one of the distinguishing features of the Swedish school of armored vehicle design. Instead of striving for absolute superiority in one parameter, engineers sought the most rational combination of characteristics. They analyzed not only armor thickness or engine power, but also maintainability, logistics, production cost, crew comfort, and the ability to adapt the design to new requirements. For a country with limited resources, such a philosophy proved much more effective than participating in the endless race of heavy tanks. The history of the IKV-72 clearly shows how quickly requirements for military equipment change. A vehicle that fully met its assigned tasks in the early 1950s required serious modernization just a few years later. However, this cannot be considered a sign of a failed project. On the contrary, the design initially had sufficient strength and manufacturability to accept new armament and continue service in an updated form. Not every armored vehicle of that period could boast such development potential. There is another detail that is rarely remembered. The IKV-72 was never tested in large-scale combat conflicts. At first glance, this might seem a drawback, but precisely because of this, the vehicle was used for decades as a kind of engineering laboratory. During numerous exercises, specialists collected data on unit service life, mechanism reliability, suspension performance, layout efficiency, and crew interaction. This experience proved far more valuable than a one-time test in a single armed conflict, since it allowed the design to be consistently improved without haste or forced compromises. In the final analysis, the IKV-72 left behind a far more important legacy than might appear at first acquaintance. It proved that even a relatively small and outwardly modest combat vehicle could change perceptions of what infantry direct support equipment should be like. It showed that success is determined not by any single characteristic, but by how harmoniously all elements of the design work together, from hull layout and suspension to armament and crew organization. That is why today, the IKV-72 is of interest not only to collectors and museum staff, but also to engineers studying the evolution of armored vehicles. Its story reminds us of a simple truth. The most famous vehicles are not always the most important ones. Sometimes it is an unremarkable project produced in a relatively small series that lays down the technical solutions that, years later, begin to determine the development of an entire direction. And perhaps that is the main paradox of the IKV-72. It did not become a symbol of world tank building, did not become famous for great victories, and rarely appears in popular films or books. But without it, the history of Swedish armored vehicles might well have turned out quite differently.